Hello. This is my part 2 of my ROP Emporium series for upsolving pawn and getting better. So this one is called Split. It's called the elements that allow you to complete red 2 win are still present, but they've just been split apart. Find them and recombine them using a short ROP chain. So what a ROP chain is basically it's just a bunch of like small assembly that we can add on after we overflow the buffer. So instead of returning to that function, the function running the code, we have to build that function kind of like, ourselves. So it says, I'll let you in on a little secret. That's useful string. This reading the flag is still present in the binary as is the call to system. It's just a case of finding them and chaining them together to make the magic happen. So let's go to our code. Okay, so for split, and I'll just place this on this side here and try to split here. Okay, so let's traverse to split. Okay, so what we want to do first is we want to verify that /bin/cat is there. So all we need to do is run strings and it'll show us the strings that are there. Oh, we can even see system. That's nice. We see /bin/cat flag.text. Okay, so we have everything we need. So let's go to gdb / let's analyze this code for a second. What we need are the ROP gadgets for return, as well as the I believe the ROP gadget to set the registers up, as well as I don't think we need that actually. I think we just need to set the register for return, and as well as the /bin/cat. So all we need to find is the buffer. So right now we can do this as pomi. Let's see here. Oh, it's the same. So we have an OX20. If you don't like reading assembly, or if you don't like having to deal with hex codes, there's a neat little trick you can do. It's called a De Bruijn sequence. So what we can do is we just set a cyclic pattern like this. We just generate the pattern, and if we run it, let's run this code, and we just paste our code here. Oh, oops. GDB, or my extension GEF, will actually help you with this, and it'll print out the this nice view of the all the registers and some of the stack. It's pretty nice. You should try it out if you can. So if we look at here, we can see the RBP register. It returns this value. So what you should do is it's overwritten. So we can just go to here and it'll calculate 32 for us, which is OX20. So it's pretty nice. Here's another neat tool, ROP gadget. So ROP gadget, what it does is it analyzes your binary and it just returns ROP gadgets that you could use. So let's see here. So we can see here we have pop. We have a bunch of pops, a bunch of calls, adds. Okay, so in terms of calling a function, what we need is pop because when you create a function, you need to initialize the registers first in assembly. So we need a pop in order to pop the previous value and create a value for the register. So let's go back to disassembly. Let's see if there's anything else we can find. Let's see. Set this useful function. Here. Oh, we have the call to system, and we have its address, and we have the pop RBP, and we have okay, so after all this, we can basically just set up our solve script. So what we need to do is we need to just pop the register, set up our /bin/cat, and then call the system function. So I have the solve script right here. So so what we do first is we just initialize the binary. We find bin cat using else.search. We set up our payload to overwrite the buffer and reach the register that controls return. We have our system address as defined here. We have our pop RDI ret gadget because we overwrite there. And then we don't need this, the ret gadget, so we construct our ROP chain right here. So what we do first is first we pop RDIs, and so we initialize the register. We set up the parameter for the system address, which is /bin/cat, and after that we just format it and we send it out to the thing. We send it out to the thing. So let's go to split and let's Python 3 solve.py. And there we go. We get the flag. So it called the code. And yeah.